of what are the concepts that you need to understand in order to make a good judgment of your processes. And we were able to identify three categories. And the idea was that you're using those to decide whether or not your current process is performing as it should. Okay, so today we're gonna go in a little bit further in terms of considering other things that can affect your process, and we're going to start talking about variability. Something that I need to mention is that from now on, I'm going to be writing on the slides, so it will be good for you to have a hard copy of the slide before coming to class, so you can make those notes on the slide. If you didn't do it for this one, I will provide you with the notes, but also sometimes, the reason I'm saying this is because sometimes I'm not able to save the notes, and in that case it will be difficult for me to post the whole thing that we discussed in class. So it will be a good for you to have the slides with you, so you, in case we cannot save the notes, you have those notes with you. Okay, so so this second topic on this area of the course is variability, and I have split this topic in two parts. So we're going to focus today on the variability, and this is material that is covered in chapter 8 of your textbook. Okay, so we're going to go through all these things today, hopefully. I'm going to give you an introduction in terms of why it's important to consider variability when we are studying manufacturing systems and the concept of variability and randomness. Then we're going to discuss what is process time variability, what are the causes of variability, what is flow variability, and finally we're going to characterize the flows and how variability affects those. And finally, we're going to talk about demand variability and flow variability. Okay, so as an introduction, we're going to look at a specific problem, and we're going to use that example through the lecture today. But before we get into that, last week we discussed what the Little law is, and basically is an equation that relates the width, the cycle time, and the throughput. And so the same throughput can be obtained with a very large width and long cycle time, or with a small width and a short cycle times. And the difference between the two, and why is that the case, is because we have something called variability. Okay, so this is the idea. Even though we have different size in terms of these coefficients, we still can get the same number, and the reason for that is because each process will have its own variability, and that will affect our final output. And if you remember the example that we discussed, the penny fab one, in which we are looking at these pennies that were going through the lines, for the perfect case, we were able to see that it achieves a full throughput of 0.5 jobs an hour when the width, or the critical width, was 4. And that was the case in which we had the line with the penny on each one of the stations. So that's basically when it behaves as the best case. But remember also when we were looking at the second example, in which we had multiple machines per stations, that one required 25/7 jobs to achieve a 95% capacity if it behaves as a practical case. And why is that the case? Again, the first process there was no variability in terms of the things that you were performing, but on the second case you start seeing some variability in terms of the processing times and the number of stations that you have. So case is, again, variability. So the idea here is that you see why this concept of variability and how that affects the process that we are going to be studying in this course. Okay, so this is the example that I was referring to. This is two machines that are called, the names of them are on the top, tortillas and hair. So these two machines are subject to the same workload. So they're going to be receiving 69 jobs a day, or about 2.875 jobs an hour. And both of them are going to be subject to unpredictable outage, meaning that they can stop working at any time during the day. But the time, we don't know when that's going to happen. But we do know that they're going to be available 75% of the time. Okay? So the difference between these two machines are the following. For the first one, the Hair X19, we're going to see long but infrequent outage, meaning that this one is not going to stop their production as often as the second one, but when that happens, it's going to take a longer time to get repaired. On the other one, the tortillas, you will see short but more frequent outages, meaning that the outages are going to happen more often, but it's going to take less time to get fixed. Okay? And we want to see what will be, with the analysis that we are going to discuss today, what of the two situations is better in terms of the output for your production or manufacturing process. So in terms of the performance, here X19 is substantially worse on our measure than the Tortillas 2000. And we want to explain why. Okay, so that's the idea for this lecture. If you start thinking about the two different difference between the two, you might conclude that having long but infrequent outage will be a better thing to have because you're going to be dealing with those less. But what the analysis is saying, or what the analysis is going to show, is that even though they are more infrequent, that is worse for your problem. Okay, so we will discuss those details in class. Okay, and why is that the case? Again, variability. Okay, so before we get into the discussion of these formulas and concepts, we first need to define what is variability and the concept of randomness. So I assume most of you, of all of you, should have some type of probability and statistic background. So you should know, at least you have heard about what is a random variable, how to compute the mean, the variance, the standard deviation, all those things, right? So that's good. So we're going to start by defining what is variability, and it basically is any departure from the uniformity. Okay, so most of the time when we think about analyzing something, we look at the average, and that's the only thing that we use to make a forecast. Let's say, okay, so everybody is getting 3.5 GPA at Texas State University, so most likely that's the GPA that I'm going to have at the end of my master's degree. But that's not necessarily the case because there's some variability inherited in the process. So there will be some students that will get 4.0, there will be some students getting a 3.0. So the average is telling you that all people will get a 3.5, but that's not necessarily the case. So, so any departure from uniformity, that's the variability. And that's what we want to consider now in our analysis. Okay, so it is closely associated but not identical to randomness. And when we think about randomness, it's anything that can affect your process that will take you out of the uniformity, if you want to see it in that way. So anything like maybe you have a worker that has a slow pace on Mondays, but it's more faster on the afternoons, and then it's slower in the mornings. That type of thing is what we call randomness. There are some types of variability that we can control, and that's what we call controllable variation. And this occurs as a direct result of some decisions. Okay, so some controllable variation, for example, very simple example, if you're making multiple products in your facility, then most likely you're going to have different descriptions for those products because they're going to be different somehow, and you need to take that into consideration when you're creating the description of the product. Okay, but there's other, and we say that we can control this because if you just produce one type of product, then you just need to create one description. But if you decide to produce multiple type of products, then you end up having different product descriptions. Okay, but there's other type of variations such that we name random variation, and this is a consequence of events beyond our immediate control. So random variation is a consequence of events beyond our immediate control. And for example, if you're getting orders from your customers, you know that you might get some orders today, but you don't know how many of them, and you don't know the quantities of them, because that's going to depend as well as the demand that the customer is experiencing in their facility. Okay, so that's an example of a random variation. And as you can think, if you think about it, all those things will be affecting your processing time and your process in terms of how many products you will have to produce on a particular week or a month. Okay, so that's what we call random variation. Now, going back to the example that I mentioned about the GPA, and if everyone is getting 3.5, most likely I'm going to get, or the average is 3.5, most likely I'm going to end up with a 3.5. That's what we call probabilistic intuition. Okay, and intuition plays an important part in many aspects of our everyday life. For example, you're driving the car, if you're going to make a turn, you know that you need to slow down unless you want to get an accident. Okay, so that's intuition, and that you know that if you don't do that, something can happen. Throwing the ball, if you want to reach some certain distance, then you know that you have to apply certain force to be able to get there. Or mastering the stock market. I'm not an expert on that, but you need to have some type of intuition in order to make decisions of which ones are you going to buy or if you're going to sell something. Okay, so our intuition is good with respect to what we call first order effects. Okay, so for first moment effects, and I don't know how deep is your understanding of probability and statistics, but if you take in some statistic courses in which they define the moments, you know that the first moment is the average, the second moment is the variance, and there's a third moment, I think it's skewness, and so on. So you can define out multiple moments of a statistic measurement. But for this particular class, we're going to be focused on the first moment and the second moment, which is the average and the variance. Okay? So what I'm trying to say here is that our intuition most likely is guided by this first moment that is the average. So we see a situation and we know this is how often this is happening in terms of the average. So our intuition is guided by that specific value. So first moment effects throughout increase the throughput. For example, increases with machine speed. So if you are producing faster, you will end up having more units. Throughput increases with availability, so more capacity. You can end up having more units processed. And inventory increases with lot size. So if you're creating more units and you're putting them into a larger batch, then you know that your inventory will be higher. So those three examples are basically guided by what we call these first order analysis or effect. So this type of intuition typically comes from acting as thought the world were, I'm sorry. Deterministic. That is without randomness. Okay, so another example can be, so you have your demand from a customer from the past week. So you know on Monday he ordered or she ordered 5 boxes. On Tuesday he or she ordered 10 boxes, and so on. So you have those values for Monday to Friday. So if you're going to take a deterministic approach in terms of predicting what's going to happen the next week, then you can, one type of analysis that you can do is that maybe the same demand is going to be repeated the next week. So on Mondays I'm going to have 5, on Tuesdays I'm going to have 10, and so on. So no variability involved in that analysis. That's what we call a deterministic approach. So we are not taking into consideration any type of randomness when we are making these conclusions. Okay, so we are thinking about just having that single number, and we're going to base our analysis on that single number. In the language of probability and statistics, such reasoning is based on the first moment or the mean or average of the random variables involved. So in the case of the example that I just mentioned, the random variable would be the demand that you would expect on the following week. If you take a deterministic approach, then you're basing that only on that single number that you have on hand, without taking maybe into consideration the last 6 weeks of the demand to make that prediction. Okay, so any questions so far? So the idea here is that we're going to take into consideration the variability when making our analysis. Okay, and you'll see where we are going in a few minutes. Okay, so our intuition tend to be less developed for second moments, or what we call the variance. For example, which is more variable, processing times or parts or batches? Which are more disruptive, long infrequent failures or short frequent ones? And that was the first example that I mentioned today. Our intuition is less secure for second moments, which is again the variance. And most of the time, one of the things that we end up doing as engineers, if we want to, for example, predict or forecast something into the future, we end up doing a regression on the points that we have, let's say, the demand. So regression analysis, basically, if you have a history, let's say these are demand points, you end up getting a line or an equation to that in order to use that equation to make a forecast. Okay? That could work, but most of the time it's not as efficient as the type of analysis that we are going to be discussing in class. Okay, so that could give you a good um, idea of how your process is behaving. But in terms of doing a forecast, sometimes it doesn't give you the best output. Okay, so that's why I'm putting this comment here, misinterpretation, for example, the regression of the mean. Very difficult to account for the variability into your process. Okay, so now let's talk about process time variability. Okay, so going into variability now, the variability is anything that causes the system to depart from regular or predictable behavior. So again, thinking about manufacturing process, sorts of variabilities can be setups, the things that you need to perform before you can run your production, like setting up the machine in terms of the parts that you need, or setting up the initial raw material that you need to run a specific process. Machine failures, material shortage, so you don't have enough to run your production for that day. Yield loss, rework, operator unavailability, workspace variation, differential skill levels, engineering change orders, customer orders, product differentiation, and material handling. And those are just few of the things that can happen that can increase your variability in the process. Okay, so as you can see, there's a lot of things that can affect your manufacturing process, and we need to take those into account when we are trying to model our process. Okay, so in order to be able to analyze our process, we need to take into account variability, and we must be able to quantify it. Okay, so now I'm going to start writing some of the equations that we're going to be using for that purpose. And we're going to start by defining what we call the coefficient of variation. This coefficient of variation is a ratio of the mean and the variance of your process, and it gives you a better understanding of the randomness in your process by taking into consideration both the mean and the variance. And it's more powerful than just looking at the mean by itself or just looking at the variance by itself. Okay, so let's define that. So this is, for this purpose, we're going to use TE, and TE is the mean process time of a job. We're going to use the standard deviation. So the standard deviation is going to be the standard, or sigma, and the coefficient of variation, we're going to use CE, is going to be the standard deviation divided by the mean, and this is what we call the coefficient of variation, or we can also use CB. So the idea here, by defining this coefficient of variation, is, for example, if you're looking at the process in which you have a very low variability and a very high average, that will give you an understanding that your process has very low variability, obviously, because the standard deviation is low. But if you're going to compare two systems, not only one, but two systems, and you want to have, let's say you have another process that has a very low mean and very high variability, then how are you going to make a decision in terms of which process is better if you are trying to compare the mean and also the value? You can end up making a conclusion in terms of the mean and making a different conclusion in terms of the value. Because most of the time what you want to have is a very low variability, and the throughput or the average, for example, a high average could be bad if your processing time is high. And you will end up looking for a processing time that is low. So the idea here is if you have these two measurements and you want to make a decision in terms of which system is better, and you have two different systems, you want to have a way in which you can take those two measurements and make it into one, so you can make a one-to-one comparison for your system. And that is what the coefficient of variation is doing. It will take these two and will come up with a ratio that you can use to compare the performance of the two systems. Okay? And that ratio is going to be based on, we'll take into consideration the variability, and also we'll take into consideration the average, the first and second moments of your process. Okay? So, note, we often use the squared coefficient of variation to make also a comparison. So in terms of the standard deviation, that would be this one, but if you look at the square, you're going to have to square this one to get the variance, and also you will need to square the average. You should end up with the same analysis, well, the same output in terms of the decision that you're going to make. Any questions so far? Okay, so this is going to be the base for the analysis that we are going to start right now. Okay, so in order to analyze variability, we must quantify it, and these are the three things, and those are the ones that I put here. Okay, so if you compute this coefficient of variation, a random variable has low variability if the coefficient of variation is less than 0.75. Okay, so if you compute this coefficient of variation, your coefficient of variation is 70% or 0.75 or less, actually less than 0.75, then you end up having a low variability process. So moderate will go from 0.75 to 1.33, and a higher variability process will have a coefficient of variation that is greater than 1.33. So in that case, basically what you're saying is that your variability is higher than your average. So you end up having a value that is greater than 1 or 1.33. So that's what we are discussing here. So this is a very nice table that summarizes the coefficient of variation and the type of system that you are looking at. And that's the same information that I basically create here with this line. So you have the three areas and what that means in terms of the coefficient of variation. So high variability red, that's bad, greater than 1.33, and in between moderate in the green area, which is the low variability and the good area for your process. Okay, so in terms of effective processing times, the actual process time are generally low variability. The actual process time is you're having a machine and you're running and processing that machine. It's that time that takes to run the machine to produce that part without taking into consideration the setups, not taking into consideration the failures, just the processing time of your part. And that usually goes here in the low variability. But now if you start thinking about the effective processing time that include setup, failures, and so on, then most likely you're going to end up having your effective processing time in one of these three areas. depending on how good or how bad is your process. Okay, so that's possible for any of the three cases. The relation to performance cases for balance systems. So if you think about the three cases that we discussed on the previous lecture, moderate variability will go for the practical worst case, low variability for the best case, and maybe for the practical worst case, and have high variability between practical worst case and the worst case. Okay, so this is basically relating what we did on the previous lecture to these three areas in terms of variability. So here's an example. So we have three machines. You're computing the average for the processing time. We also compute the standard deviation, and we can get the coefficient or variation by dividing this by this. Okay, and we get the three different values. And as you can see here, what making this variability goes high, for these two cases actually, the variability is going very high. But that is because we have 3 points, and those are the ones that I highlighted, that are making that variability go very wide, right? And for the second case, it's not as bad as the third one, and you can see why the third one is getting that high variability, because you have a 500 on numbers that are most of them less than 10. Okay, so you can see the effect of having those outliers into your processing time. So most likely here what happens is you end up having a failure in your process, and that processing time is taking into account that time for repairing the machine. So the question now is, can we measure the coefficient of variation this way? I mean, is this giving us the real or representing what's really happening in our process? I mean, if you end up having just this without, what will be the difference? Okay? Unless this is happening often, you can say, oh, this is not representative of our process. So making this analysis as it is right now may not give you the right recommendation in terms of analyzing your process. And that's what I'm getting into right now. So the answer is no. We will consider our rare events properly. So as it is right now, with the tools that we have, we might end up making a wrong conclusion, because the analysis right now is not considering the probability of having these rare events. Okay? So we need to go a step further in terms of adding more concepts to be able to account for the variability in the right way. Okay, so that's what we're going to start doing now. We're going to look at the causes of variability, and this is going to be split in three different parts. Okay, so we're going to start with what we name natural variability, and this is variability without explicitly analyze cause. Okay, so variability without explicitly analyze cause. So these are things that are happening in your process, and very difficult to get a reason for why is that happening. Okay, so this is the variability inherited in the natural process time which excludes random downtime, setups, or any other external influence. Some examples: operator pace. So you can have an operator working very fast at some point and then maybe changing that pace in the afternoon, or maybe he's sick, so he's not feeling very well, so you will see a different pace on that day. So all that is inherited in the natural process, and it's very difficult to quantify and to find a reason for that. Material fluctuations. Maybe you have a supplier that is not producing as many units or having an issue with his plant, so you might end up having less units. That's something that you cannot control. Product type, if not explicitly considered, and product quality. So if your process is having a lot of defects, there's some things that we can do to find what's happening. Maybe we need to tweak some of the machines or other things. But again, the idea here is to see that those are things that are not, we cannot find a cause right away. Okay, so there's no explicitly analyzed cause for that type of variability. So the observation is natural process variability is usually in the low variation or LB category. So even though we cannot find a specific cause for it, we know that it will go to the low variation area of our analysis. Okay, so now we can define the coefficient of variation of a natural process time, and that's going to be CO and again, they're going to use the same three inputs. So we're going to have T0 as our mean process time. The standard deviation 0, which is going to be the standard deviation. R0, which is 1 over the mean process time, is our base capacity. In terms of the rate or parts an hour. And then we can define the coefficient of variation as the standard deviation divided by our mean process time. But as you will see, this would also be the same as this. So the natural process times are only the starting point for evaluating the effective processing time. And in real production system, workstations are subject to different detractors, which are not taken into consideration in this particular step of the analysis. Okay, so we are not now focusing only on the natural process. So the variability on the pace of the operator, or something that we cannot easily find a cause for. Okay, so in real production systems, we know that we need to take into account the machine downtime, the setups, and everything that cause a variation in our final output. And that's what we call the detractors. Okay, so we're going to start looking at two different types of detractors for our system. Okay, the first one is what we call variability for preemptive outage. Okay, so most capacity and these outages are basically breakdowns that can happen in your process, like failure and so on. So most capacity planning tools used in industry accounts for random outage when computing the average capacity. So this is done by computing the availability, which is given by the following equation. So first, we need to define two parameters. MF is the mean time to failure. And MR, which is the mean time to repair. And this availability equals the mean time to failure divided by the mean time of failure plus the mean time to repair. Okay, so now we're going to take into consideration the availability of our process. So our analysis is not just based on assuming that we have our products available. So we know some breakdowns are going to happen, and that's going to give us an idea of how often our process is available for production. And we're going to use this equation to compute that. Okay, obviously, you're going to need to have some estimates of the mean time to failure. So how long it's going to take on average to get another failure in your process. So maybe every 2 days, I should expect a failure to happen. And when that happens, most of the time we take an hour, 2 hours to get the machine repaired. Okay, so now defining the effective mean processing time, we're going to use TE, and this is going to be equal to T0 divided by the availability. Okay, so now we're going to use our effective processing time is going to take into consideration the natural variability and also the availability of the process. Okay, so it's taking into account the breakdowns of the system and also the natural variability of the system. And the effective capacity rate, RE, is going to be equal to M divided by TE, and A times M divided by T0, which is going to be equal to the availability times the baseline capacity. Okay, so now we're going to use these concepts to define our some of the things that we started discussing at the beginning of this lecture. Okay, so remember the example of the two machines in which we have the here X19 and the torque years. So if you start computing some of the coefficients and values that we discussed in class already, we can get the effective time of processing, including the natural variability. We can get also the standard deviation, which is 3.35. So for both of them, this is going to be the same. So that means if you compute this coefficient of variation, you end up having the same coefficient of variation for both. Now, if you look at the mean time to failure and mean time to repair, as we mentioned already, this one is going to have longer periods of time without the failure, but the time for repair is going to take longer. Okay? And this one will have more often, so it's happening every 2 hours, but the repair time is also low. This coefficient of variation of the repair, we are not assuming, or we are assuming that the repair is going to have no much variation. It's going to take about the same time to get it done, so that's why we have a coefficient of variation for the repair is just 1. Okay, so we are basically assuming that that's not going to affect our analysis. And now using this information, we can compute the availability for both of our machines. And the availability, you'll see, again, this is mean time to failure divided by mean time to failure plus mean time to repair. So for this case, it's 744 divided by 744 plus 248. And I'm doing this in minutes. So this is 0.75. And you get to the tortuous, or the second machine. It's the same thing. You're gonna get 114 divided by 114 plus 38. So this is 0.75. So as you can see, by looking at the availability by itself, we cannot make any conclusions because they end up having the same availability. Okay? So even though they have these coefficients that are different, if you look at the availability of both of the machines, it's the same. Okay, so we need to go and do other things, like considering the downtime variability of effects. Okay, so there's no difference between the machines in terms of the availability. Okay, so now we are going to start taking into consideration the downtime. So when breakdown occurs, how is that variability in terms of how often these breakdowns are happening, how long is it taking to repair them, is affecting our actual variability in our process. So here I have some equations, and this again is based on the same concept that we already discussed. We can compute the effective time of the process, and we can compute also the variability, the effective variability of our process by using these two equations. Okay, so if we want to compute the coefficient of variation in terms of the variability, then you know that you have to divide this by this. And if you compute that, you're going to end up with this expression right here. What's important of this expression is that this part right here is saying, or is taking into account the variability in terms of the repair time. Okay? So you've seen here, there's a coefficient for the mean time to repair, and that is linked to the effective processing time of your process. Okay, so failures are going to inflate the mean, the variance, and the coefficient of variation of effective processing time. And this is all conclusions coming from this expression. The mean increases proportionally with the availability. The standard coefficient of variation increases proportionally with the mean time to repair. It also increases proportionally to the coefficient of variation of the repair square. And for constant availability, long infrequent outage increases the standard coefficient of variation more than short frequent one. Okay, so that kind of guides us with our first question for this lecture. Okay, so for constant availability, which is what we have in this example, long infrequent outage increase the standard coefficient of variation more than the short frequent ones. Okay, and we're going to see that now. So if we look at the coefficients that we have for both of these machines, we can compute the mean process time as follows. So this is T0 divided by the availability. So in this case, that's 15 minutes divided by 0.75. So this is 20 minutes. So if you take into account the availability, that is what the effective time of processing a part. Now, to compute this coefficient of variation square, or the effective coefficient of variation square, we need this. So CO2 plus 1 plus CR square times A times 1 minus A times MR divided by T0, which is the expression that we defined. Okay, so this is going to be equal to 0.05 plus 1 plus 1 square times 0.75 times 1 minus 0.75 times 248 divided by 15. And this gives us 6.25. If we perform the same analysis for the second machine, then we have T0 divided by A, which is the same, 15 divided by 0.75. This is 20 minutes. And we have the same equation, CO squared plus 1 plus CR TR squared times A times 1 minus A times MR divided by T0. So in this case, we have 0.05 plus 1 plus 1 squared times 0.75, 1 minus 0.75 times 38 divided by 15. And this is equal to 1. So based on this square coefficient of variation, we can see that this one has a high variability and this one has a moderate variability. So let me put it here, high variability, moderate So in terms of this coefficient of variability or coefficient of variation, X19 is more variable than this machine. Okay? And as you can see, yes. This one? Yeah, this is square. I think that's already square. C0. Yes. Yes, so you have to square it out. Yes. Can anyone do this in your calculator just to make sure that we have the right answer? Okay, that's a good point. 0.95. So when you put this, yeah, that one will be 0.9. So 0.0 squared plus 1 times 0.75 times 0.25 times this is how much? For this one? Something wrong there. Let's see. Okay, so as you can see, this one has high variability and this one has a moderate variability. So we're getting more into, you can see that having longer, even though you're going to have less failures happening, they're not as often as those, but since you're going to have a longer time to repair, that kind of adds more variability in your system. If you think about, I mean, I'm getting ahead a little bit here, but if you think about the width of your process, um, it's important that you have enough width for your process in case a failure occurs, because let's say a failure occurs on the first machine of your process. If you have enough width working process on the next machine, you can continue working on the other machine, and you're going to end up having more production that if you didn't have enough width into your system, right? So that's the whole idea. If you find the right width for your system and an unexpected breakdown occurs, you can still have a good production at the end of your process. But it's more easier to keep a low width into your process than having a high width in your process, meaning that you have a lot of parts waiting in an area of your process. It can interrupt other activities in your manufacturing plant. So having a low width is important, and that's why when you have shorter repair time, you can run your process with a lower width because you know that you're going to be repairing those failures faster and continue working into your production schedule. On the other side, if you don't know if this is happening not as often, but when that happens, you need to be prepared to have a very high width in your system to account for that particular part of the process, then that added a lot of variability because it's very difficult to keep that weight into your same process. So that's the idea. then everything connects, okay? So shorter period of time for repair allows you to have a lower width that will allow you to run your process in a steady state, you can say. But when you have this very long period of time in which you need to repair your machine, then in order to run your process in a steady state, you're going to have to keep a very high working process into your process. Yes. So as you can see, having shorter repairs and more often favors a shorter repair than having a long wait time for the next failure and high repair times is better. Okay, so here I'm showing the impact of variability. So in both machines we have the same arrival, 2.875 jobs arriving per hour. So here it's 90 with even more variability than torture. How these affect the width and the cycle time? We're going to go into those details on our second part of this lecture. Okay, but I just give you an idea of what's the problem. But we're going to go into the analytics behind it. So we're going to show it to you with the numerical analysis. So we talk about the preemptive outage. Now we can talk about the variability of the non-preemptive outage. And these represent downtimes that will inevitably occur, but for which we have some type of control as to exactly when it's going to happen. So some control. Oops. For example, when a tool starts to become dull or needs to be replaced. Okay, so now we know that it's going to happen at some point, and we can start preparing for it. So we have some control over that. Maybe we can wait until the next change of production. We're going to start producing another product. We can use that time to replace the tool. We don't have to stop the process until that happens. So process changeover setups can be regarded as non-preemptive outage when they occur due to change in production. Has changes in the product. Okay, so we can have some type of control on this type of outage as opposed as the preemptive outage. So as we did for the preemptive outage, we now have another type of analysis for this. Now we're going to take into account the average numbers between setups, average number of jobs processed between setups, and we're going to have the average setup duration and also the standard deviation of the setup time. And again, we can compute the coefficient of variation for the setup, then the effective time or the effective processing time for the parts, and the effective coefficient of variation when we take that into account. Okay? So I think what I'm going to do is, I don't want to go into these details. I think I'm going to stop here, and we're going to continue from here on our next lecture, which is going to be on Thursday, but on Thursday we're going to go into the arena second lab. So this we'll continue this topic on Tuesday of next week. Okay. So on Tuesday of next week, we're gonna start looking at the analysis of how to deal with these non-preemptive outages. Any questions? I think I can post some homework, at least for the first parts of these lectures, so you might expect to see some homework due on Tuesday next week, based on these concepts. Any questions? No. So I'll see you on Thursday. And I recorded, let me see if this is going to work. Yeah. Yeah, so as I was saying, I'm trying to save the notes. It's not letting me. But I do have the video.